First order of the lab. Of the lab is as follows. We have a quiz will be due in 2 days or tomorrow, I think. Check it out, tomorrow or after tomorrow, the 15th or the 16th. Quiz number 4. Quiz number 4, which is covered the last 2 labs we have done, which is 9 and 8. Quiz number 10 will have only one experiment, which is VSEPR. Again, why I'm doing this? Because you'll have 5 quizzes. Your quizzes average is expanded, so this chance to survive the quizzes is more likely. And the other thing is VSEPR is one of the most difficult topics inside the final exams. I don't know why, but students are failing this in the lecture as well in the lab. So let's do this one here. We'll start with Lewis dot structure, and we'll start with VSEPR, and then we'll do some examples. So today, what you have to do, I put for you the template here. How to do you'll do the same way we did the lab report. First of all, your introduction, what's this lab is all about, your data, your procedure. Your procedure is just doing some theoretical Lewis dot structure and determining VSEPR, the shape, molecular shape of molecules, and you will fill your data is here. This table here has to be filled and submitted. So here it is. I added that for you here. This is your data here. This is, you have to fill it. Now, I can understand it will be very hard to do, very hard to do with the hand. So what you will do here, you bring this page here. Listen, guys, you bring this page here. You will do it per hand, because it's a lot of drawing of structure, okay? And then in the data sheet in your lab report, you paste the picture, or you can Google the Lewis dot structure of the compound itself. You have my permission. So for example, here is ammonia, IClO4. So what I will do, copy and paste this structure, copy and paste, and then I will go in Google Chrome or whatever. So I'll go and try to find, I will say here, paste, and then this is the compound Lewis structure. So let me switch. Let me share the Google Chrome. So it said Lewis dot structure here. So I come and then just with this snippet here, I come and do the, this is the Lewis dot structure of the molecule. I can make it even better than this by clicking on this, then I will get, this is just the, or you can just draw here, it is not the YouTube, you can take the images, images search, and here we are, there is the lots of structures of the compound itself. One of them is in this one here. One of them is this. So get to the source. You get to the source. Text snippet here. Okay, new, and just take this one here. Okay, guys, I'm copying this one here. Copy. Then I have to stop sharing here. Then I will go and share my sharing this one here. I say, well, the structure of this is here. That's the area of the structure. So I put the Lewis structure here, thumb, and then paste the whole thing and space here. Everybody's following? So either or, because it's very hard with you to draw those per hand, or you have to have a special software. Even though if you have special software, it takes for you hours to do those. So you have my permission to use the web to Google the Lewis dot structure, the correct one for the compound, or you can just take it out and do by your hand the whole thing and then paste the whole thing. But here you can just add whatever, how many valence electron total, how many, all this stuff can be filled. This is your data here. This is your data, 2 pages. And we have to determine the molecular shape, the Lewis dot structure, the total number of valence electrons, and how many regions or how many groups we have, how many non-bonding. We'll go through this together. But at least the angle here is if the compound is polar or non-polar. So we have to determine this. So let's go back, starting with our Lewis dot structure. Well, Lewis had developed a very nice way to describe the bonding among the covalent compounds, especially the covalent compounds between nonmetals, and by representing the valence electrons as dot, correct? Those dots, even for elements, you can do. So Lewis for sodium is 1A. For example, here, look at this. I hope it's the pen is working. It is. So sodium here, for example, sodium has 1 valence electron. So it has what? It has 1 valence electron. So you just write sodium and then one dot means 1 electron, correct? Now, for example, carbon has 4 valence electrons. Carbon has 4 valence electrons in group number 4, which is, this is group number 4, and it has 4 valence electrons. So carbon will be, then you'll have 1, 2, 3, and 4. So you get the idea? So Lewis came up with the idea is to represent the valence electrons as dots. What is the meaning of valence electrons? Well, valence electrons, those electrons are found in the last outermost orbital in the atom. Within an atom, you have orbitals, correct? 1, 2, 3, 4, 5, up to 7. Now, we know that it can go beyond 7, but we have only 7 periods. We have only 7 periods. We are interested in 7 orbitals only, not go beyond this. Although we know that 8 is there, 9 is there, all those orbitals are present. So you look at the last orbital, so it looks like it is in the 4th. So it has, if you look at this, if you look like this, it looks like 2s2, 2p2. So this is the valence electrons of, that's the orbital that they 2s2, 2p2. So the sum of this is 4. So the sum of this valence electron are 4 and found in the second 2, the second orbital for carbon. So he will tell you those 4, I can represent them as dots. And then when I start connecting those dots to make a single bond or double bond or triple bond, then it will be easy. Then I'll come here and then say, okay, let me just go here and I say I have a carbon here, correct? So here it is, and here's carbon. So I can make carbon here. So here it is, I can make a single bond. So by connecting the 2 dots from 2 different carbons, I make a single bond. Okay, I can move one of those here up and make a double bond. So here it is. Let me take this one here out. Move this one, those 2 here. And I say, well, I move them here. I move them here instead. One is here, one is here, correct? So I can make out of this double bond. You see that? So there is one here, sorry. Forgot one. There's one here. I'm sorry, the color is not correct. So here it is. Now, can I make a triple bond out of this? Yes. I can move one of them here. I can move this up to here, move the other one up to here, and they will be looking one here, one here. So the bond will be looking as, so this one will be looking like this, triple bond. And then one electron can be connected to what? To one hydrogen, for example. If I have hydrogen here, I can connect hydrogen. So here it is. I can connect this one here to hydrogen. So you can see this is the way how is Lewis he was thinking about describing or establishing single, double, triple bond, correct? So this is just connecting the valence electrons of different atoms and then build the double, triple, and single bond between the atoms. Now, you have to recall this is for covalent bond. This is not for metal. The metal is not involved in this the Lewis-Dot structure. The metal will be different because one will be giving, one will be taking. If I look at the metal, then I have another story here. So if I have sodium, correct? Sodium has 1 valence electrons, correct? Then I have chlorine here, has 7th group, 7 valence electrons, 2, 2, 2, and 2. Now, can I put this one here? Can I put this one here as, so can I put this one here as this one here? That's wrong. This is wrong. So this is, we are not doing this for the metals. The metals will not make single bonds, double bonds or triple bonds. The metals are donating. This is wrong here. So this is absolutely wrong. Big mistake. So how we do the ionic compound? We know how to do the covalent bond. How do the ionic? Well, it turns out to be the ionic will be looking like this. If I have sodium here, this is sodium here, correct? And this is chlorine. Chlorine has 7 valence electrons, 2, 2, 2, and 7. So it turns out to be the sodium is giving away its valence electrons. Those metals in ionic compounds, the metals are valence electrons donor, and the non-metals are acceptor for those valence electrons. So I have Na had lost 1 electron to chlorine, so Na plus, and the chlorine is taken 1 valence electron, so it will be 8, 2, 2, 2, and 2, and then it 2 here, and it will turn out to be negative. This is the ionic compound of sodium chloride. This is the Lewis-Dot structure of sodium chloride. So whenever I have ionic compound, I have to have a metal is giving away its valence electrons, and then the non-metal is taking in this valence electrons. This is the Lewis-Dot structure, the correct one. Not the covalent bond. The covalent bond will not have plus minus. If I have a double bond, then everything will be looking like this. This is the double bond, correct? And this is hydrogen is connecting to the double bond. This is ethylene. So here it is. This is hydrogen, right? So if I have a triple bond, then I have, this is triple bond. This will be looking like this. If I'm looking for single bond, then I will be looking as single bond here will be CC, and then all of it is H, 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 H. So all of this is hydrogen, 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 and hydrogen. So, do I have any positive or negative? No. There is no donation. The covalent compounds are sharing valence electrons, while the ionic compounds are transferring valence electron from the metal to the nonmetal. So this is correct for the ionic. This is ionic here. This is ionic compound or bonding, and those are all of those here are covalent. So you can always look at the difference between those. So this is this first. So now let's look at the this is about the Lewis dot structure and how to make the single, double bond, triple bond, correct? And here just an example we talked about some examples here. So I wanted to read this how to do the Lewis dot structure. When I start a Lewis dot structure for a compound, covalent compound, the ionic compound is easy because the metal is giving away its electron, will appear positive. The non-metal will take in the valence electron, will appear negative. But the covalent bond or bonding is difficult. You have to consider some of the rules. One of the rules is the electronegativity. Somebody will tell me what's the electronegativity is all about? What is electronegativity? Come on, guys. Electronegativity is the ability of an atom to pull out electrons from adjacent atom within a chemical compound. If you have, for example, fluorine, and you have hydrogen, in this compound HF, hydrofluoric acid, the fluorine is more electronegative, so the fluorine will take in the hydrogen, will take in the not the hydrogen atom itself, but the valence electron. So the valence electron of hydrogen will reside more towards fluorine. So we'll put all the time the most electronegative atom away from the central atom as much as we can. So that's one of the rules of how to make Lewis dot structure. Lewis dot structure, your electronegative atom has to be put all the time far away, and they cannot be put closer to each other. Compounds, they have two electronegative atoms together near each other, most probably they'll turn out not stable, like peroxide. You have two oxygen near each other, so they are highly electronegative. To try fighting each other, each one would try to pull out valence electron from the adjacent atom, the adjacent oxygen. So they start fighting. So the molecule is not stable, correct? This is the first one we have to know. The Lewis dot structure, I mean, when you write this that structure, oxygen is always -2. Come to where hydrogen is always +1, except when it's connected to metals. So, and if you look at it like this here, you can see how you can make those here. So, example, methane, CH4. How I can do the Lewis dot structure for methane? Well, I start with carbon as 4. It is correct. And then I have 4 hydrogens. So each hydrogen will have 1 valence electrons, correct? And each one is 1 hydrogen, and each 1 hydrogen. So first of all, you have to always, there is no electronegative atom. Those are very, very moderate electronegative atoms, not that high. So then next is to come and connect your single bond, single bond, single bond, single bond. So you have 4 single bond. This is the Lewis dot structure. You have to check this is really true. You have to calculate the total valence electrons. So total, the sum of the VE, total valence, VE means valence electrons. So you have 1 carbon and 4 hydrogens, correct? So 1 carbon has 4. This is 4. 1 multiplied by 4. And hydrogen has 1 valence electron, 4 multiplied by 1. The total is 8. Let's count them. So let's count those. Here it is, 1, 2. I make one single bond. 3, 4. Another single bond. 5, 6. Another third single bond. 7 and 8. 4 single bond. This is the total is there. That's the way you can check if your work is correct. If by chance, if the total is not corresponding to the structure you have drawn, something is wrong. Some electrons, some valence electrons are missing. So you have to go and recheck your Lewis that structure. So this is our what? This is our Lewis dot structure of methane. Now we have 4 single bonds. When we have 4 single bonds, we say that we have 4 units, correct? Or we can have, we call this the same thing, all the synonyms, 4 regions, right? So all those are the same thing. So, or another synonym is 4 groups, correct? So you treat the single bond, with the double bond, with triple bond, with lone pair, the same thing, correct? So we call 4 units, 4 regions, 4 groups. They're meaning the same thing. So we have 4 single bonds. If we have even different, we'll see some examples here. Now, let me go to see how we are looking at the methanes here. Let me go for sharing here. I'm stop sharing here. And I want to share with you the, Okay, let me, that's not, okay. Yeah, I want to share with you this one here. I hope it's sharing it. So let me see, let me stop sharing, just to make sure that sometimes it does not share the one I need. So, okay, it does share. So this is a real model, and this is just a model, and this is real model. So we can do real molecules, correct? And let's click on it, and you can see how the whole thing is. How is the molecule? But I like to go back and look at the model itself. Let's go back and look. So let me take the model to show you how I build. This is 2 atoms, correct? Single bond, 2 single bond, and 1 atom in the central, the middle called central atom, correct? And 2 ones. I will add to this. So I need to know, let me just double check that I'm in the right place. Sometimes Webex does not like to share the ones you need. Now, let's look at this. I have 2 single bonds and 2 different atoms. One in the middle called central atom, correct? This is called central atom. If it will allow me to maybe, this is central atoms. As I said, today there is no lab. Today theoretical stuff. So this is central atom, and those here are called terminal or edge. Terminal or atoms at the edge. Terminal. terminal atom. Yeah, I apologize. I used the okay, terminal atom. So I have one, please. So I have two of those, correct? Now I will start adding. This is FET. This is Colorado, University of Colorado at Boulder. Very nice software simulation. So now let me take this one out and see if I add another third one. First of all, let me remove this. Remove this. I say, what is the molecular geometry and what is the electron geometry? Both of those are linear. So the shape of this linear. The central atom has the least electronegative, does not pull out electrons. And the terminal, we can put the most electronegative one, correct? And we can calculate the total number of valence electrons. We can do everything. We have two shapes. We have molecular geometry and we have electron geometry. What's the difference between molecular geometry and electron geometry? Somebody will tell me what's the difference between them? Well, it turns out to be molecular geometry. You ignore all the lone pairs. See here, this is lone pairs here. Let me just write here. This is a lot of lone pairs here, correct? And this is single, double, triple bond here, correct? So if you just consider the single or triple or double bonds, then you speak about molecular geometry. If you consider everything, including the lone pairs, then you speak about what? Electron geometry. So that's the difference. Electron geometry is looking at the whole molecule, including what? Including the lone pairs. The molecular shape or geometry does not include the lone pair. So now we have a linear what? What's the shape? VSEPR. VSEPR stands for valence, valence shell, electron pair, repulsion. Valence shell, electron pair, repulsion. So this method here will show you that the shape of a molecule will come out or will happen or come out after a lot of repulsion between the valence electrons among themselves, and the molecule then will obtain the least situation, the least position when all these repulsions are really very, very weak or at minimum. So when the molecule reaches minimum repulsion forces among the atoms, then we'll have the final shape. And that's what we say VSEPR is about, the repulsion between the valence electrons, correct? Repulsion among the valence electrons, and the least repulsion that will control the shape of molecule. Now, why we have to study this Lewis dot structure and the VSEPR? VSEPR is a method of determining the shape of the molecule. Why is this very important? But you will tell me why it's very important. We have to study this here, and we have programs show us about this. Well, it turns out in the medicine, in the pharmacy, those type of molecule, when you play with them here a little bit, see here. So if you have a tumor somewhere here, there is a tumor, for example, somewhere there is a tumor here in the cell. So you'll try to design, you design another molecule that's had, correct? It's like another one here, whatever, maybe another one here. So those type of this atoms here build like a net. They will encapsulate the tumor. So therefore, the shape of a molecule is very, very important design to fight any intruders inside the body. So the designer, the chemist, or the pharmacist, mostly is the same thing. So the pharmacist is taking the chemistry and see the influence of the chemistry on the bio system, in the living system. But the chemistry will design this medicine. So you will design somehow that the whole tumor is encapsulated within this net of atoms, so it will not go out. Are you following me here? So most of the time it's very, very important um, in medicine. Now, even purification of H2O, when you have to purify your H2O, you need sort of any bacteria or anything inside the H2O to be encapsulated and removed. How you do it? You have to have the shape of the molecule that will take out this type of bacteria out of the H2O, so you can verify your drinking H2O. So that's the one of the applications or two applications for H2O. So let me add here now another one. How many we have now? 3 single bonds, correct? So if we have 3 single bonds, correct? Let's look at this. We have 3 single bonds, and with this said, the trigonal planar and for the molecular geometry and electron geometry. What's unique about this, as long as you don't have what? You don't have what? Lone pair. If you start having lone pair, then you are asking for a problem. So you will have what? You'll have a problem. So if I take this one here, guys, look. I take this one here, remove it, remove one, and I introduce myself here too. Can you see this? Here it is. I move it out. Now I introduced to you one lone pair here. See the lone pair here? Now, is the electron geometry equal to molecular geometry? No. If I remove here, if I take this one out of consideration, then I have, this will be bent. If I consider it here, if I take the whole molecule as is, then I speak about trigonal planar. You get the idea? So the shape, the molecular shape or geometry is excluding the lone pair. So I have what? I'm just considering here those here, bent. See here? I'm considering those here. This one here. So this is bent. This is the molecular. But if I include the whole thing here, okay, so this one will be then trigonal planar. Correct, guys? So now let's go further. I will take this one out and remove this one here. I will add another, see here, 3 of them. There is no lone pair. So the trigonal planar will equal the electron. So they are electron geometry. They are both geometries are the same. If you look at there, both of them are the same because there is no lone pair. I will add another one. So this is trigonal planar. So I will say the middle here, bless you. So this one here is said to be, I put this one here, for example, X, and put this one A, whatever. I can put this one A and X, whatever this is A, whatever your book is doing. So those are terminals. Terminals, and this is central. So if I look at this, this is X, the VSEPR code, A, how many A's? I have 3. So XA3. XA3. I have 3 terminals and 1 central atom. So this is XA3 is always will be, the molecular will be trigonal and the electron will be trigonal, correct? So let's take now this one out and add another one. This will be tetrahedral. So I have, this is my X. Whatever the number, whatever the code is, it's up to you. You can put them A here, B, whatever. That's just, I put just here for you, A. So the formula here, the VSEPR code is XA4. So without lone pair, this one here is called what? Is called the shape of it, the molecular or electron geometries are tetrahedral, no lone pairs, correct? Now, let me add, take this one out. Let me add now another one. How many we have here? How many? Can you see it? Let's look at this again. Can you see it? This is trigonal planar. Trigonal planar. If you look at the whole thing here, maybe I can't be. If you look at this is triangle here. 1, 1, and 1. And so this is the base is triangle, trigonal. Trigonal means triangle, correct? Bipyramidal, it looks like we have two pyramids. We have bipyramidal, we have two pyramids. One, this is the top of the pyramid, okay? And the base is here. And the second is the opposite here, here, and maybe with another color here. Here it is, here, here, right? And here, oops, here and here. So this is two pyramids together. So two pyramids together. So bipyramidal. So again, there is no what? There is no, if you see, there is no lone pair, correct? How about if I add another one? So here it is. I decided to add another one. What will be this? So if I want to move it here, see here, I can move it all the way. So what is this then? What will be? That will be what? This 8 means what? I have, let me see, watching all of them. This is octahedral. This is what? Octahedral. So there is no lone pair. The shape of the geometry is, as long as there is no lone pair, the electron and the molecular geometry, both of them identical and both of them octahedral. Correct, guys? So, and the will be A, B. How many terminals? We have 6. 1, 2, 3, 4, 5, 6. 6. So AB6 code, not AB, but A with X, correct? Let me just take this one out. Here it is. X, A, 6. This is A. All of those are A's here. A, A, A. Sorry. A here. Another A here. Another A here. And this is your X here. So AX, this is octahedral. Now, let's introduce ourselves the lone pair. The lone pair will bring us a lot of headache because it will alter it will make a difference. It will alter the shape of the molecule. So let's take this one out and start over. So let's take out 1, 2, 3, 4. We started here. We said both of them linear, correct? Now, how about if I add this one here? So this one here will be, what will be? Well, let's see. Let's see here. This is my A. This is my A terminal, correct? This is my X central. And this is called lone pair, E. So the code here will be A or X, A2, E1. How many lone pairs? 1 lone pair, correct? This is, the molecular one is bent because I'm excluding this. So the molecular is exclude lone pair, exclude, take it out, exclude lone pair, correct? So with this one here, the electron, You'll say the opposite, include lone pair. So here, you have to include what? The lone pair, include lone pair. When I include the lone pair, this one will be still the same thing, correct? That's the code for the whole molecule. That would be XA2E2. So when I take the lone pair out, it will be pent. Take the lone pair out. So if you take the lone pair out, it will be, that will be this one is pent, no lone pair, pent, correct? So this one here is pent. When you include it, there will be 3 of them, will be trigonal planners. So let's take this one out. And now, how about adding another one? So this one will be, let's put the code. Let's put the code. This is A. This is A. This is X. This is E. This is another E. So this is X central atom, A2, and lone pair how many? 2. So the code is, so again, if I exclude the lone pairs, the both of them out, I'm having what? Still bent. So the molecular geometry is still bent. But how about if I include the lone pairs? I have a tetrahedron. I'm including all those all those lone pair. I have tetrahedron. If I exclude them, I have a pent, correct? With the code XA2E2. So let's do another one. Let's take one of them out and add one. What is this? That's ammonia, correct? Look at this. This is ammonia. Now, if I look at this ammonia, how about the molecular? So I have to exclude, look at this. I will exclude this one here out. And then I'll say, okay, I'm just looking at those 3 without, because the molecular, I have not to include this one here. So this one here, because it's like this, correct? Looks like this. Without showing this. So this is trigonal pyramid. It's a pyramid. See here, this is a pyramid here with a base. Is a triangle. Trigonal pyramid. It's a pyramid with a triangle base. This is the base is triangle. But if I include this one here, like the one here, then I will have here, this is the central atom. This is one lone pair. This is another lone pair. This is another bond here, another single. So this is the lone pair here. This is the lone pair. And there's 3 atoms. So here you have, sorry. So, and so this is tetrahedral with the lone pair. So the electron geometry is tetrahedral, because I added what? I added the lone pair. This is electron geometry. If I exclude that the whole lone pair, this is trigonal pyramid, correct? This is trigonal pyramid. So let me take this one out. How about if I take this one out, okay, and add 2 of those? This one, trigonal bipyramid, correct? Everybody's following? How about if I decide to get one of them out and put instead one of them out? So how many we have here? 1, 2, 3, 4, 5, correct? I'll take another one out. And how about this? What is this? Look at this, guys. The shape is called CHEM. So, so that's the molecular shape. Called what? So, because I can transfer this one here. Transfer it here for you. So this one here, I will exclude this one here out. This one is out. I will consider this one here, 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 and here. This is a seesaw. If I include the whole thing here together, I will include this one here. So this one will be included. And this, and this, correct? With that, not with this one here. So, and then the whole thing here together. So this one will be trigonal bipyramid, the same thing like before. This one is trigonal bipyramid. Are you following me here? So excluding the lone pair, we have seesaw. Including it, we have trigonal pyramid. Correct? Let's do another one. Let's take one of those here out and add another one. Wow, look at this, guys. Look at this. I can do it this way. How about I can do it this way? How about I can do it this way? So this is a T shape. So I can I move it this way in front of me? Yes. Look at this. If I remove, guys, look, if I remove the lone pair, I have T shape. So look at this. One here and one here. 90 degrees, T shape. That's the molecular what? This is the molecular geometry. If I include all of them, then this will be trigonal bipyramid. Will be what? Trigonal bipyramid. The same thing we did before. So you can move this one here, will be trigonal bipyramid. Now, how about take another one out? I'm not sure if it will allow me or not. Take one out and add one here. What will happen? Wow. Look at this. Look at this, guys. I have 3 lone pair. Now, are those inside the table? Yes, I gave you one table here. You can check the table out. So now I remove all those and I'm considering the molecular, and it turns out to be the molecular one is just what? Linear. Is what? Absolute linear. Because it's not including the lone pair. But if I look at anytime I look at trigonal bipyramid, then I will have what? I will have trigonal bipyramid if I include the lone pair. Are you following me here? Everybody's okay now? Everybody's okay? Now, let's see if you can follow me here. We'll see. Let's remove all those here out. This out, this out, and this out, and add this one here. Take this one out and add another one. This is carbon dioxide. This is C. So here it is. I will say this is carbon. This is oxygen. Double bond. This is oxygen double bond. So if I look at this, there is no lone pair. So whenever there is no lone pair, then the electron and the molecular geometry are identical. So linear, linear. This is what? This is linear, linear. How about, let's do the triple. So let's take this one out. Okay, add triple here. And take this one here. Add 2 triples, 1 triple here and 1 single here. So this is like you have a carbon, carbon, something looking like this, and add, that will not work. So something looking like this, for example. So this type of will be what? Still linear, correct? It's still linear, there's no lone pair. And what you have to look at, that the single bond is treated as triple bond. How many regions we have here? We have 2, correct? How many regions we have here? 2. So let's go back and look if we can recall here. Let's take this out here. So let's put this one here. How many regions we have here? 2, correct? Add another one. How many regions we have? How many groups? 3 single bonds, correct? So how many? 3. So if I take one of them out, I add 2. How many regions we have? We have 3. How many? 3. 1 single bond, 1 double bond, and 2 singles. We treat them all, correct? So here it is. Take this one out. Add this one here. How many regions we have? 3. You treat the lone pair as single bond, as triple bond, and double bond equal. So this is a region here. So you can go here and say, okay, this is a group. This is another group. This is another group attached to the central atom. So you have 3 groups, regardless whether it's a lone pair or single bond or triple bond, correct? Last thing here, and then I'll let you to do the table here. So let's take this one here and tell me about the polarity of this compound. Let's take this one out. So is this polar, this molecule, what do you think? Polar or non-polar? Polar or non-polar? If I have, for example, it is carbon, and here's hydrogen, and here's hydrogen. So is this polar? The answer is not polar. Why? This compound called symmetrical. Symmetrical means they are the same, opposite direction but the same. So if this is the whole thing here, so this is symmetrical. They are the same. So now if I take this one out, symmetrical are non-polar. So this is non-polar. So let's add another one. Add another one. Take this one out and add another one. Now all those are the same, correct? Like the compound, like this is boron, and this is hydrogen 3. So you have 3 hydrogens. This is hydrogen. This is boron. This is hydrogen. And this is hydrogen. Is this compound polar? The answer is no. Why? Because it's symmetrical. The terminals atom are the same all over the molecule. So the electronegativity difference is determining the dipole. So the pulling of the dipole is totally, so if it's pulling like this way here, it's pulling this way here, and it's pulling this way here. So you will see that the 3 dipoles are identical but opposite to each other in the time and space. So they are opposite to each other. So this is non-polar. How about if I add another one? So like carbon, hydrogen, 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 hydrogen. So CH4 is what, polar or non-polar? This is again non-polar. Why? It's symmetrical. All over the terminal atoms, all over the place are identical. So this is non-polar. Okay, guys? So now, suppose I want to change one of those terminal atoms. I said, okay, so let's change this one here. And let's do, here's carbon, here's hydrogen, here's hydrogen, but here is chlorine here, and this is hydrogen. So this compound will be CH3Cl. Is this compound is polar? Yes or no? The answer is yes. Why it is polar? The answer yes. Polar. Why is polar? Because now the atoms all over the molecule are not identical. We have 3 hydrogens and 1 fluorine. So this has to be polar, and that's really it. This is chloroform structure. Chloroform goes in the blood and makes the people dizzy and sleepy. Therefore, it's dissolved in H2O, the bloodstream. So therefore, it's polar. Are you following me here? So this is just to the whole thing. Last more thing, and then we'll stop here. Anytime, guys, anytime I have, just blindly, I have a lone pair, I have a compound with lone pair here, correct? The presence of the lone pair here will force the molecule to be always polar, always, here guys, always what? Polar. Always polar. As long as I have lone pairs, always polar. So let me take another one. Take one is out here. This is polar. Can you see it? This is polar. Add another one. This is polar. Take one out, correct? And add one. This is polar. Moved one. Put one. Add another one. This is polar. Anytime I have a lone pair, the molecule will be always polar. The molecule will be always polar, regardless. Anytime I have a lone pair present, the molecule will be polar, correct? So I think this is the most important part of the whole molecule here. We'll go and stop sharing, and then I will go to share the Microsoft Word here. So this is about the methane. We went ammonia, went through a lot of H2O bent, so carbonate, that's that structure of carbonate. And you can look at the whole, this is the same thing with hydrogen. So we treat the single bond, double bond, triple bond the same as one region, one unit, one group. And then we went to the central atoms A. I put the central atoms X. It does not really matter. So, but this is an example here. And this is your, you can use it, but the final exam, this one will not come. So make sure you understand the whole arrangement, so you can understand what's really going on. This is very important for the quiz I will put. This table is very important for the quiz. So if I go here, I give you some examples here. See the lone pair? The CO2 is linear, trigonal planar, it's examples of them here. When you start introducing the lone pair, you make the compound is polar, and the molecule will be changing from trigonal planar to pent. You can see here, so will be pent angled or pent. So this is just an example of this one here. So let's start doing at least we'll do some of those here, guys, and then I'll let you maybe do the rest at home. So let's do the second one. Open your place here, open your computer, whatever you have. Everybody has this one ready here? Everyone has this? You can, everyone has a computer. Everyone has a computer? No? Everyone has access to this? No? No, yes. How many of you has no access? You have no access? You have access. Anyone has no access to this? Somebody will tell me? Guys, anybody has access to this? Okay, so let's do for me ICl4 minus, and let's finish it up. We'll finish at least a couple of those, and then I'll let you go. So how many total valence electrons of ICl4 1 minus? How many total? So iodine is the 7th group, correct? So I will do for you this one here. Iodine equal how many? 7 VE, 7 VE, valence electrons, correct? Fluorine has 4 multiplied by 7, correct? 7 valence electrons. Those are 28. I can make them smaller here, so we can. That's maybe 10 or 10. So, however, you have valence electrons is 28, but you have the negative charge 28 here. 1 negative charge. Okay, so one negative charge. Whenever you have one negative charge, you have to add this charge. If you have positive, then you have to subtract it. If you have a negative, then you have add 1 charge. So how many total now we have? Well, it turns out to be. So we have 7 plus 28. This is 25. 25 minus 1 because it's negative, correct? You have 25 plus 1. That's total is how many? 26 VE. So we have 35, 36, guys. 7 plus 28, that's 36. That's correct. 35 plus 1, 36. That's 26, 36. So we have total of 36. Total of what? 36 electrons. So pairs of bonding electrons on central atom. So how many pairs you can take? Well, we got the looking at this, we did the electron structure. I mean, use that structure of the compound. How many lone pairs we have? 2 sets, correct? Look at this here. Look at the iodine in the middle. Look at the iodine in the middle here, guys. So here it is. How many sets? Then that will be 2, correct? So here will be 2 sets. 2 sets here. So this is 2 sets. Pair of bonding. Now bonding here, bonding, guys, 4. Bonding 1, 2, 3, 4. Sorry, that's my mistake. 4. Non-bonding is 2. That's has to be exchanged. The non-bonding is 2 sets. The bonding is 4. We have 4 single bonds, correct? So and now, what is the electron geometry? What is the molecular geometry? Well, now if you take this, if you take those out, correct? Are these following? So if you take those are out, the lone pair are out. So what you'll have? You have tetrahedron, correct? Makes sense? So the without the electrons, without the lone pair. So it will be, so here it is. So with this it will be A, if this is A, whatever, this is A, this is X. So you have A, X, 4, that's for the molecular geometry. For this one here, A, X, 4, and then E2. E2. Correct? Are you following me? 4, 5, and 6. So this is for electron. Electron here. Geometry. Because you have to include this electron, you have to include this one here. For the molecular one, this one here is molecular one. You have to exclude, take out the valence the lone pair. So this one here will be. So somebody will tell me EX4 will be tetrahedron, correct? So this one here will be tetrahedron. Right? but you have include all of those. This one will be octahedron. So let me check the table. Oh, sorry. Octahedron. So because this is the sum of those two here, the sum of those two plus 4, 6 regions. So come back and look. We can. So we say one is tetrahedral, that's the molecular. One octahedral, that's the electron. So let's see here. Octahedral, we have 2. This is the one you are looking for, correct? Here, guys. This is the one we are looking for. We have either in the middle, 4 carbons all over, correct? And this one will be, if you look at this, the 4 one, not tetrahedral, will be square planar, and the other one will be octahedral. The electron will be octahedral because you have to include all of those. So you have to include octahedral is, see here, it is, guys. The answer is here. I gave you the answer. This is the compound here. This is the structure. And it's not a tetrahedral, but it is square planar because you have to look. Take this one out. Take this one out. Take this one out. And it turns out to be like this, square planar. 4, only 4, you consider 4. But if you consider the whole 6 here, this will be octahedral. So the electrons here will be, you include all of them, that will be octahedral. You take those out, will be square planar. So let's go here and write the answer here. I give you all the stuff here. So electron geometry number 1. Number 1 electron geometry is octahedral. Octahedral, I don't know why it's in the middle. Okay. And this one here has to be the table. Octahedral. Okay, so number 1 is octahedral. This is, oops. So just put this one here, octahedral. And this is, okay. This is electron. So the molecular is square planar. So square planar. So, and if you look at this, if you look at the angle here, go back and look at the angle here, you will see that's 90 degrees, like it's a square. All of this 90 degrees. The molecular one, 90 degrees. That's 90 degrees. The other one is totally different from there. So it's totally different. It's the same thing here. We have number 6, octahedral. This is just tell you in general, does not tell you the whole thing. So it's 90 degrees. Okay, so it is polar or non-polar. Take this one here. Yes or no? Yes. Why? Because it has 2 lone pairs at that. If we have a lone pair, then it has to be polar. Yes. And this is because of lone pairs on central atom. So you can make it smaller even. 1. So it is. So this is the answer of. So here it is. This is octahedral, and you can. This is electron geometry. And this one here, square. So this one here is square planar. This is the molecular geometry. So Mg and Eg. So you can put here electron. This is your Eg. And this is your Mg. And this is okay, guys. So then you can put them this way. Okay, let's do do for me this the 1, 2, 3, number 3, CH3Cl. We did that one. This is chloroform, correct? So what will be? How much total electrons? Somebody had calculated how many electrons they do have? We have 1 carbon. We have 1 carbon. Come on, guys. 4, correct? 4 valence electrons. Then you have 3 hydrogens. 3 hydrogen, 3 multiplied by 3 by 1. This is 3 multiplied by 1 is 3. Reduce this one here to 10. Okay, so and chlorine, how much? Chlorine 7. Chlorine is 7. So 7. So total is now so how much is the total? 3 and 4 is 7. 7 plus 7 makes 14. So total is 14. So how many bonding of electrons are on the central atom? How many bondings? We have 4, correct? We did that. So suppose you can't draw, just Google this. We did this one here, if you recall, a couple of minutes ago with the simulation. I'll copy this. This one will not appear, but I'll copy this. All right. I need the image of the with that structure of this compound. Okay, so give me this. I can choose anything I want. This one seems to be okay. Take my snipping tool here and take this one here out. I like this one here. So here it is, copy it. Then I go to my open my thing here. Then this is okay. So this is, you have my permission to do that. That's has nothing to do really with copyrights, because the copyright is very important when you start making profit out of it. For educational purposes, the judge will tell you you can use it. We are not just copy-based for the educational purposes, that's fine. But if you want to make a book and use this one here, we have to have permission. You cannot just take it and put it in a book like this. No, you have to have permission from the author, from the company, or from the publisher, or from anyone that's done this. So this is how many regions we have? We have 4. This is the central atom. So how many? Let's go back. This is 1 region. This is 2nd. This is 3rd. This is 4. 4 single bonds, 4 regions, 4 units, 4 groups. Okay, so this is very important. So now, how many bondings? We have the bonding one are 4 single bonds, 4 single bonds. So this one is 4. How many lone pair? We have no, there is no lone pair on the carbon. 0. So this is 0 on the 0 here. That's no lone pair, right? On the central, we don't care about, guys, here, look. We don't care about those lone pairs here. Those are not on the central atom. Always we look at this. Do we see any lone pair on the central atom? This is the heart and the core of the molecule. But the central atom, we don't really care about this. So 0. Now, what is question? Do we have a lone pair? No. Then electron geometry and molecular geometry will be the same. So those are 4 regions, correct? And if you look at this, this is, if you do, I don't know, if say this is A, Central atom is A, this is X, whatever you can tell them. So this is X, and this is X. This is AX4. So AX4, this one here, tetrahedral. What is this? Tetrahedral. 4, that will be tetrahedral. So I can look at this up. I have 4, correct? Here it's number 4. It is number 4. No lone pair, correct? Same thing. That's like this one here. No lone pair. CH4. So this will be tetrahedral. So I come here. It's no lone pair. There's no lone pair there. So the yellow stuff, there's no lone pair. So I will say this one here will be tetrahedral. Tetrahedral, and this is my EG, correct? Electron geometry, and it is the same thing, tetrahedral, because there is no lone pair. Tetrahedral for my MG, molecular geometry. So both of them are identical. So what is the angle of this? Well, it has to be the same thing like the ammonia. It is 109. See here, just copy and paste this one here. And you can read this one here from the top. The angle, I think maybe the angle is not here, but the angle is 109. I should give you the angle here. If you look at this, it is, can you see here? So tetrahedral angle is 109. I see it, tetrahedral is 109. So it is a tetrahedral, so it has to be 109 here. So I'm just copy and paste. The question, it is polar or non-polar, yes or no? Yes, why? No, it is polar or non-polar, yes. Why? This one here, yes, because of, there is no lone pair here. Because of what? Because the molecule is not symmetrical. The molecule is not symmetrical. What do you mean? This means the molecule, it has different terminal atoms. So 3 hydrogens and 1 different, 1 chlorine. So, okay, guys. So how about this one here? One more, and then I'll give you the ozone, and the rest you can do it at home. So you can work on them. So BF3, so BF5. So I will copy this one here, and then I will go to the web and see what the Lewis dot structure. Paste it. So you can write this one here. You can take any one of this. So whatever you like, you can take those here. You can draw this one here with your own, but it will be very hard with your hands to do this. So here it is. Copy. And you can come back and look. So this one here would be, this one is the Lewis dot structure, because the total here, phosphorus has how many? How many? Phosphorus has, 1 phosphorus has 5, correct? Valence electrons. And fluorine has 5 of them multiplied by 7, correct? This is 35. So 35 plus 5, next one, total is 40. So 40, total 40 valence electrons. Everybody's following? Total is 40. So now you ask yourself, here it is, how many pairs of bonding? we have 5 single what? We have 5 single bonds. So it has to be 5 regions, 5 units, 5 groups. So it's 5 bonding, 5 single bonds or 5 bonds or 5 bonds. So 5. Then do we have a lone pair on the central atom? No, we don't have any lone pair. Do you see any lone pair on the phosphorus? No, that's a 0. So if you have the case, this is A. So if I look at this, no lone pair. So this is A, central atom, and X is 5. AX5. What will be is that? So what is AX5? If you don't know, you go back and look into this, correct? Go back and look into the whole thing here, AX5. So you come here and then you look at the AX5, correct? This is 6. There is AX5. See here, trigonal bipyramid. So here there's no lone pair, correct? 5. 1 lone pair, there's none. All bonding. See here, let me just. This is 4, 5 of them, all of them bonding. So the trigonal pyramid, trigonal what? Pyramid. So the both of them will be trigonal pyramid, and trigonal pyramid for both, for the molecular geometry and for electron geometry, both. So it is, and I'll put this one here. Oh, we have that's wrong. So let me cut it out. I have to put here, sorry. So here it is, will be trigonal pyramids. Okay. This is AG, and so this is EG, as well as will be just copying and paste this one here into this. This one will be MG. So oh, here we did not do the angle. The angle is 4. Let's take this one out. So this one here, if you look at this, this is tetrahedral, correct? The tetrahedral is 109 degrees. This is trigonal bipyramid. What's the angle of trigonal bipyramid? What's the angle of it? Well, we will have two. Listen, guys. We'll have 2 of the angles because we have a trigonal. It can have 120. Listen, guys, the back. So we have 2 types of angle here. Look at this, guys. Here, look. So if you look at the trigonal bipyramid here, you have this and this an angle, correct? And then one far away, those are from here, correct? This is this angle, and then the other one is this. So you will have, if you have just both of them trigonal pyramid, and you will have 2 angles. So this is might be not beyond your, beyond your table. That's not even the table given to you, trigonal pyramid. But trigonal pyramids, they do have, here this trigonal have 2 of, yeah, they brought you 120 and 90. So 120, that's the triangle planar, and 90 degrees. So if you look at this, it does have both of those here. Let me just a trigonal pyramid. I thought there's nothing there, but this is there here. So copy this and paste. So is this polar? The answer is no. The answer is no. Why is not? Why? Because all terminal atoms are identical, the same, and this molecule is said to be symmetrical. This molecule is said to be symmetrical. If it's not symmetrical, then yes, the case. So let me just this one a little bit. And okay, guys. So any question you have? Guys, on any question? Yes. Yeah, so if the central atom has a lone pair, then this molecule will be polar. If the terminal atom is the same all over, it's non-polar, right? So like BF5, all of them fluorine. Now, if I change this one here, suppose now, I put this one here, look, I put this one chlorine. It is polar or non-polar? Yes, now it's polar. Why? Because we don't have all the atoms, all the terminal are identical. This is non-symmetrical. This now with the chlorine instead of the, I'm taking this fluorine out, right? Replace it with chlorine. So this now, this one will be this is now called polar. Why? Because the molecule is not symmetrical. Different what? Different atoms, different terminal atoms. So this will be terminal, correct? You want me to do ozone? Ozone one of the three, correct? So let's make ozone here, and then I'll call it off, and then you will have to do for me the rest of the data sheet. You have to tell me if they are polar or non-polar. And you want me to upload this for you? The college? Upload it? Okay, so yeah, I'll upload. So let's do the last one and then I'll let you go. Ozone. Ozone has 3 oxygens, correct? Let's do it together. Ozone has 3 oxygen. And oxygen is 3. The balance of oxygen is 6. So 3 multiplied by 6. Let me just see. Decrease the. So let me go for 10. So yeah, I don't want just to go home without knowing nothing. So I'm just explaining everything for you. So 18. So total is 18. Okay, guys, 3 multiplied by 6. Oxygen in the 6th group. So valence electron is 6. That's 18. So ozone will be 1 in the middle, 1 terminals. I can tell you the molecule will be, the molecular geometry will be bent. So now suppose you have problem how to draw it. You put 1 in the middle, 6, 1 in the 6, and then try to make single bond first. If it's not satisfying octet rule, make double bond. So it will be one of them double bond, the other one is not a double bond. So let's do here the thing here, ozone, O3, and you will see the Lewis dot structure of ozone is 1 double bond, as I said to you, 1 single bond. So here is a good one here. I'll take this one here. Here it is. I'll take this one. This one sounds very good. So this is the Lewis structure. You have my permission, okay? And we are copying from, don't need the copyrights because we are not selling or making profit out of it, just for demos for our purposes. So, but if you want to do any official stuff, then it has to go through legal channels. So you have to contact the authors, the company, tell them that you are borrowing this, and they might ask you for money or whatever. So, but anyway, for our purposes, it's okay for educational purposes. So we are doing here the Lewis dot structure of ozone. So we can even make it bigger so you can see. So if you look at this, what will be the whisper code for this? Look at this. We have A, this is A, correct? This is X, and this is X. So we have A, X, 2, correct? 2 terminals. However, we have here a problem here. We have what? We have lone pair, E, E what? E1. So AX2E1, that will affect, first of all, about the polarity. So let's take this one out. Now we know that's AX2, that's the code of it. It is polar or non-polar? Well, we go for the central atom. Since the central atom has a lone pair, then what we do here, it has to be polar. So we'll copy and paste this one here, yes. Copy and paste this one here, copy it, and then we'll write in front of it here. It is polar. It has to be polar because it has one set of lone pair on the central atom, correct? Now, how many bondings we have? We have two bondings, one single, one double bond. So how many? We have here one, and here one. We have two. So therefore, bonding how many? Two. Bonding is two. How many non-bonding is one? One set is here. One set is non-bonding. So we write this one here is, this one here is one. So one is non-bonding. So now, what is the original, what is the electron geometry and what is the molecular geometry? Are they identical? No, because of the presence of the lone pair on the central atom, the electron geometry will be different from the what? From the molecular. So if I have something looking like this, guys, look, the same thing we did. So this is oxygen. This is oxygen. This is oxygen. Don't worry about double bond. This is double bond, for example. But however, we have here one set of lone pair. So if we move, correct? So if we look at the whole thing, how many is this? So it looks like, so if we include this, include the lone pair, so this one will be trigonal planar. 3 will be what? The electron one will be trigonal planar, correct? But now if I want to take this out, the lone pair out, it is 1. I took the lone pair out, double bond and single bond. So the lone pair is wiped out. It's not considered. So this one here is bent, correct? So this one here is bent. But if I include this one here with the lone pair here, the top of it, and this one is here, this is double bond. So this one will be then, this one will be trigonal planar. So trigonal planar, right? This is your E electron, Eg. This is your Mg, molecular geometry. Correct, guys? Can you see it? So, therefore, you can see here, this is bent, this molecular. So you exclude the lone pair. When you include it, then all of them, this 3 will be AX2E1, that will be trigonal planar. So here it is. So let me take this one out and write it here. So the trigonal planar, this is your Eg, correct? And make it smaller here. And your pent is your Mg. It is polar. Yes, it is polar. So now, if you look at this, this one. Now the angle here, if you look like this, trigonal planar has what? 120, correct? The trigonal, but because of the presence of the lone pair, This one will be squeezed, will be less than 120, correct? Will be less than 120. I will be less because of the presence of the non-pair, maybe 180. So less than the trigonal planar 120, less than 120, less than 120, less than 120 degrees. Why? Because of the presence of lone pair on the central atom. Okay, guys. So, wanted to upload this? Upload it right now. Any other questions? So you will do then. You will do this one here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you'll post it in your data sheet, right? If you have problems with them, come and see me in person or email me, or we can set a Webex meeting together. Any question you have? I'll stop recording in a couple of minutes. So any question you have? That's all about the lecture today. Is not a lab per se, it's a more theoretical background. And I hope I covered most of the stuff. You should by now have covered this one here in the lecture as well. Okay, guys, I'll stop the recording. I will just before we leave, let's do some dates here, mentioning some dates. So next week will be Thanksgiving. You'll not come here. There will be the whole not the whole college, but the college will be on the side of administration open. They will close just Thursday and Friday, but they are still open. But classes are closed. No faculty will be there, but the staff and the administration are there. So if you have an issue, financial aid for the next semester or so, you can do that before Thursday next week, Thursday next week. So don't come next week. Now, there is a quiz coming. You have 1 day until tomorrow or after tomorrow. You have to do it. And I will post for you a quiz number 5, just whatever we have covered today. And the stuff we have discussed, I'll upload it to you in the iCollege. So you should be able to see it. Everybody following? Then when we come back, we will have quiz number 5 and the review. You have to come to the review because this is not my exam. I did not make it. The exam is college-wide, and I saw the exam. It's a lot of calculations. And the exam has two, we'll talk about the exam in the review. The exam has 2 components. One is theoretical, one is practical. One experiment you have done in the very famous experiment you have done. So they will ask you about the concentration of whatever the compound is, whatever. So this experiment you have done it in the lab, you will be asked. So the exam has 2 components. One is written, and one is practical. So you have to do an actual experiment. And the exam for 2 hours, the final exam. And I prefer when you come back after the Thanksgiving, we'll have a review. And then after that, we'll have final exam. So review and then final exam. Correct, guys? So any question you have, I'm here open. You have any question? Any question? So don't come next week as Thanksgiving week. You come next, after the Thanksgiving will be review, and then after that will be final exam. Right? And it has 2 components, one written and one practical. Right? So, okay.